All right, chapter 17, CP3, not to be confused with Chris Paul. This is Circles and Polygons Essential Learnings. Today we're going to talk about points of concurrency and their properties, as well as solve systems of equations using substitution only. Okay, so let's get rolling. All right, here are points of concurrency. 3 or more lines that have a point in common. These are not concurrent. They're not concurrent because they don't meet at the same point. These are. There's your point of concurrency. We're going to talk about a couple of special points of concurrency today that happen within triangles. All right. Let's see here. I think I talked through it all there. All right. If I place the 3 angle bisectors of a triangle inside that triangle, okay, here's an angle bisector, because it takes that angle and what does it do with it? Cuts it in half, right? Cuts that in half. Here's another angle bisector, cuts that angle in half. Yeah. Where do you think that third angle bisector is going to go? Yeah, it's going to cross in that point of concurrency right there. And that's not perfect, but that point of concurrency is actually the center of this circle inside that. Yep. It's the very center of the circle inscribed in that triangle. Isn't that satisfying? Now, watch this. This is kind of cool, too. That point, wouldn't you agree, is equidistant to every point on the edge of that circle? Yeah. So that point is equidistant. That green point is equidistant from each of these, where the circle touches the edge of the triangle. That's called this green point. This green point is called the in-center. That's the name of that green point, the in-center. So the angle bisectors of a triangle form the in-center. Okay, let's keep going. Our definition, right? Here's some of the work shown, some of the vocabulary involved with the angle bisectors and the in-center. The angle bisector concurrency conjecture, right here in this rounded box here, is the 3 angle bisectors of a triangle are concurrent. Right? They meet at one point, this point right here. And the point of concurrency, there's not a whole lot of groundbreaking material in those first couple sentences. It's called the in-center. Okay, we're just kind of breaking down using vocabulary what we just talked about on the previous page. Correct. So properties of the in-center. The point of concurrency of the angle bisectors. It is equidistant from the 3 sides of the triangle. And it's equidistant from the 3 sides. And the center of the circle that touches all sides of the triangle is the inscribed circle. So it's the center of the inscribed circle. And the center of that inscribed circle is equidistant from the 3 sides. Here's a kind of an application of the in-center. Let's say that there is a 5K race, right? 5K race. And for whatever reason, the designer of this race wanted the race to be a circle. So we start over here and go this direction, and we finish right here, coming the opposite direction, right? They want to put an aid station somewhere on the course so that if somebody has an injury, they can be tended to as quickly as possible. So they put it in the middle, right? In the in-center. Why would they put it in the in-center? So it'd be equidistant to any one of the roads. Right? So that's the in-center. Most of the time, stuff in the real world happens in triangular shape. I mean, you could argue that something's quadrilateral in nature, but you could split it up into triangles, and you can work, well, four-sided or more. But you could split any shape up into triangles, and then therefore you can find the optimal distance to an edge of a triangle, which then could help you, in this case, in the aid station situation, right? Or gas stations, right? With regards to highway traffic and stuff like that, it gets a little complicated, but it is related. Okay, so there is a reason that things are in the place that they are. Okay, let's talk about our next incenter, formed by the perpendicular bisectors. Okay, so a perpendicular bisector is perpendicular to a side and does what to it? What does bisector mean? Cuts it in half. So if I take this right here, this segment, and I bring it over here, I want to cut this side in half and have it be perpendicular. I'm talking about this side. I cut that side in half and I make that segment perpendicular to it. All right, I want to cut this side on the opposite side in half, this one right here. That would be right about, would you agree, about there? Yeah, cut that in half. So I want this segment and this segment to be the same. So my next bisector, perpendicular bisector, should cut that in half and be right about there, yeah. Okay, and then this side right here, I want to cut it in half. That's probably right about there. Pretty close. Oh my goodness, getting old. Thanks. Thanks. Oh, and look at that. Conveniently, what do? They meet at a point. Now, this point is special for a different reason. This point right here is called the CIRCUMCENTER. It's the center of the inscribed triangle. Okay, so before we said that the in-center was equidistant from the three sides of the triangle, now it's equidistant from the three what? What pieces of the triangle? The three angles, the three corners, right? Okay, so the perpendicular, I'm going to shorten this, perpendicular bisectors give us the CIRCUMCENTER. All right, application of this one. The other one was, when we looked at the in-center, we said it's equidistant from, oh, where did it go? Oh, it's further down on this slide here. Okay. It's equidistant from the three, let's say, paths or roads, right? Sides, if you will. On this one, it's equidistant from three what? Angles, or we could say locations. Right? So, for example, let's say you have three high schools. We're not going to name this one, but it's green, so we know. And we have this other one, and it's red. Yeah, we know. And we have this awesome one, and it's blue, right? We have these three high schools. And let's say there's three track meets going on at the same time at those three high schools, and they want to put some kind of aid station in between those three. Now, there are three locations, not three roads. This is different than the in-center. This is called the CIRCUMCENTER. So it's not necessarily the center of the circle inside the triangle, it's the center of the circle. It'll be right there, right? That's the CIRCUMCENTER. Right? Imagine I connected this with a triangle like that. Yeah.
Are you saying that the circle is the paths, kind of? Or,
no.
Okay. That that is just like this area of like the, I don't know.
Okay, so let's draw the in-center on the same one. Okay, so can we agree that's the circumcenter, the center of that circle, right? Equidistant from Minnetonka High School, this red high school, and this green high school. Now, if we were to have a 5K going between the three, well, it would be a lot more than 5K, but if there were a race going between the three, then we'd draw this circle here, and that would give us an entirely different center. That would be equidistant from these points.
Do we want the black circle to be equidistant from, but it could be,
We want them to be equidistant from the actual locations because the people aren't moving. Right? You got it?
yeah.
So the black one's not the center of the circumference.
It's the center of the circle. So the black one is the circumcenter, the blue one is the in-center. Okay, so now this is kind of cool and goofy, but let's take three other high schools. Let's take the red one that we know. Let's take ours, obviously the best. And let's take, we don't say these names out loud, are you kidding me? Let's take, there's another purple one down here. No, I'm thinking of a different one. But if I were to draw the circle that enclosed these, because the circle's got to go through each of those locations, right? So where would the aid station be? So that it's equidistant from each of them.
Would it be like right there?
It'd be right here.
Well, that's the
But it's equidistant from each of the schools.
Oh my gosh.
Because if I did this, if I did a race between the three, obviously the shortest, the in-center would be here. It'd be equidistant from there, it'd be equidistant from there, and equidistant from there. Right, but then the red school would be closest. If nobody's moving location, we need to have that aid station equal distance from each of these. So my drawing isn't perfect to scale, but each of those black lengths are about the same. We don't want any school to be closer to the aid station than others. I mean, not that we would say, well, I guess, yeah, we don't want them closer to the aid station than we are. Come on. Just kidding. That was a joke. Kids laugh at those, yeah. Okay, so let's talk details on this real quick. We're just going to fill in the information here that we already know. Three perpendicular bisectors of a triangle are concurrent, and their point of concurrency is called the circumcenter. All right. Yep. Okay, so properties of the circumcenter. Point of concurrency is made up of the perpendicular bisectors, equidistant from the three vertices of the triangle. Right. Center of the circle touches all three vertices in the triangle. It's called the circumscribed circle. Note, the circumcenter may fall outside of the triangle, like we talked about in that third one, right? Right, in that second example. When this triangle is what? What do we need to know about this triangle when that happens? What's true about that angle? It's bigger than what? 90. So if it's obtuse, if it's an obtuse triangle, like we saw on this slide, right here, this diagram right here, that blue triangle is obtuse. Therefore, the green dot fell outside of the triangle. It's still inside the circle, it's still the center of the circle, but it fell outside that triangle. Okay, so in the cities of Safariville, Maxwell Heights, and Tutstown, Mr. Todd Hill must have done this one, they want to put in an ice arena that is equidistant from the three high schools. Which point of concurrency should they use? So you got Safariville, Maxwell Heights, and Tutstown. If they want to put in an ice rink that's equidistant from those 3 points, consider those the corners of the triangle, right? So I draw a circle. What would that center right there be called? The circumcenter. Yeah, it's the circumcenter. The circumcenter is equidistant from the 3 Vertices of the triangle. Think of it as high schools, right? Not paths, but high schools. Locations where people would stay, not where they'd travel around. In the city of Bologna, that's probably Mr. Boleyn's hometown.
Is Maximus short for, or is Max short for Maximus? The Max.
Ooh, I don't know. That's a good question. That's a good question. In the city of Bologna, there are 3 roads that make a triangle. Eagle Avenue, Skipper Road, and Gusty Parkway. The mayor of the city wants to put a drinking fountain in that is equidistant from those 3 roads. Well, I've got Eagle Avenue, Skipper Road, and Gusty Parkway. You got Gusty here. You got Eagle here. You got Skipper here. Okay, what I would do is I'd draw a circle in the middle of that, and this point would be equidistant from each of those roads. That's called what? This right here. The in-center. That's the in-center. All right, so here we go. Oh, shoot, I got more of these. Altitudes. Okay, hold on. Let me see where I want to go with this. Okay. All right, I'm going to quick run through the altitudes. The altitudes are segments that go through a vertex and are perpendicular to the opposite side. So now instead of cutting this side right here in half, it's not going to do that. It's going to go through that point. Okay. The next one will go through this point right here. And the third one will go through the opposite vertex over here. That right there, that point right there is called the orthocenter. It's formed by the 3 altitudes. Now, the way I remember this one is when you go to the orthodontist, do they typically give you like some kind of laughing gas? Yeah. If you're having a procedure done, at the dentist, they give you something, right? And you kind of feel like you're floating. Okay, altitudes, where's that? Way up in the air, you're floating. Orthodontist, orthocenter. So you're kind of loopy. Yeah, that's how I remember the name of this one. Okay, and there's no practical application to this one, like there was in the previous 2. Okay, so we don't have to go through a word problem. You just need to know the altitudes form these segments, these green segments right here are called the altitudes because we named them that. So if it goes through a vertex and is perpendicular to the opposite side, we call that an altitude. It's like a height of the triangle. Right? That's the height of the triangle. We call it the altitude. The altitudes form the orthocenter, which is this point right here. Smiley face time. Bam. There's the orthocenter. Okay. All right. I'm going to breeze through this slide right here real quick. The altitudes of a triangle are concurrent. All right, we've done this on the last 2 slides. And their point of concurrency is called the orthocenter. I'm not going to write it all out because I want to get through this. The altitudes in the orthocenter may fall outside the triangle when the triangle is, again, obtuse. All right, so here we go. We've been taking lines and we've been finding where they cross. How do we do that algebraically? This chart right here we'll fill out as the week goes on next week. But how do I find the point where 2 lines cross? Well, I can draw them, but that might be a problem because I might be terrible at drawing straight lines. Some kids use their arm as a straight edge, and that's a terrible idea. Okay, so solving this system is not the best way to do it graphically, but when we use substitution, that's probably the optimal way. So what I'm going to do is I'm going to take what x equals here, right? X equals this, and I'm going to plug that in for x over here. All right, so if I plug that in for x right here, I would have 2 times what x was on the left side. And now what you might notice is what's the only variable involved now? Y. So now I can solve for what y equals. I'm going to distribute the 2. So I get 6y plus 14 plus 5y equals 3. Let's combine some like terms, yeah? So how many y's do I have? I got 11y. If I subtracted 14 from 3, negative 11, what would y equal? Yeah, y equals negative 1. Okay, so I got half of the coordinate where those cross. These are just two lines. All right, this is a line right here, and this is another line right here. I want to find where they cross. Well, I know that y equals 1 where they cross. I got to figure out what x equals when they cross. So I'm going to plug this negative 1 back in here for y. So x equals 3 times negative 1 plus 7. So x equals negative 3 plus 7. So what does x equal? 4. So those two original lines, where do they cross? They cross at the point 4, comma, negative 1. Whoa, is it possible that maybe, like, I don't know, these two lines could be those special lines that we saw in the triangles, and this point right here could potentially be either the in-center or the orthocenter or the circumcenter? So you could have located maybe potentially on a map where you want to put your aid station. Yeah. Okay. So that would be solving a system of equations using what we call substitution. All right. I'm going to call that good for today. Those of you who want to jump in and get one more attempt in, you got about 20 minutes left in class here. Oh, I forgot to stop recording. Like, subscribe, comment. 34 more subscribers and $19 to GNC and Mark Wahlberg bumper sticker.